All right, kiddos, let's keep going with this derivation here. So just as a reminder, the equation for electrostatic force is K times Q over R squared, right? But the work that was done by that force is a force times distance. And so this denominator, one of the distances goes away. There's no longer a squared as a result of that force times a distance. Okay. This distance has a special C abbreviation here for critical distance. It's the closest the alpha particle could have gotten to the gold atom. And so that critical distance is the distance from the center of the alpha particle to the center of the gold. All right. And so if we wanted to calculate this critical distance using this equation, we totally could, just putting in more specific abbreviations. So we could do the kinetic energy is 7.68 mega, so times 10 to the 6 electron volts. Okay, to get that in joules, right, we need to multiply by the charge of an electron, 1.6 times 10 to the minus 19. Okay, and we set that equal to K, which is 9 times 10 to the 9, times the first charge. The charge of the alpha particle is 2 times the elementary charge. And the charge of the gold is 79 times the elementary charge, right? Where these guys are 1.6 times 10 to the minus 19. Okay, and then over that critical radius, which we're looking for. Okay, so generically, to solve a problem, if we weren't talking about gold, if we were talking about any other element, the nucleus of any other element, we could say that the equation is, right, the energy, initial energy of the alpha particle is equal to Coulomb's constant, right, times the charge of the alpha particle times the charge of whatever atom it is, right? So to get the charge of the nucleus of any other atom, we take the elementary charge and multiply it by the number of protons. Remember, that's abbreviated as Z over the critical radius. Okay, and it turns out that when we do this math, the critical radius is 2.96 times 10 to the negative 14 meters. Right, that's as close as you can get to the center of the gold nucleus. And so Rutherford assumed that that was the radius of the gold nucleus, right? That was the highest energy alpha particle that could get the very closest to gold. Okay, so he is assuming, based on that the critical radius is the radius of the gold nucleus. Okay, I'm going to skip this for just a moment to define really quickly the atomic mass unit. Okay, you may have heard of this in chemistry, but the atomic mass unit is abbreviated with a lowercase u, and it's 1/12 the mass of a carbon 12 nucleus. Okay, so atomic mass unit is 1/12 of the mass of a carbon-12 nucleus. So it's like essentially the mass of a single nucleon for a carbon-12 nucleus. It's kind of the average mass of a carbon or of a single nucleon, excuse me. So in your data booklet, if you were to look in there, you would see stuff like the mass of a proton is 1.673 times 10 to the negative 27 kilograms, or it's equal to 1.0073 atomic mass units. Okay. And so with that, the 1 atomic mass unit, right, you can turn atomic mass units into kilograms if you just do a little bit of math. 1 atomic mass unit, you take the mass of a proton divided by its mass in atomic mass units, and you get atomic mass unit is 1.66 times 10 to the negative 27 kilograms. Okay, so that's a mass of a nucleus. Is about the number of nucleons times atomic mass unit. Okay, that's a good approximation of the mass of a nucleus, right? How many protons or neutrons, right? Uppercase letter A times the atomic mass unit. Okay. So now let's talk about nuclear density. All right, so what we're going to do is assume that a nucleus is a sphere. It's not perfectly a sphere, but we're going to make that assumption. So we can say that the volume of the nucleus, right, that spherical volume is proportional, right, to the number of nucleons that are in there, right? The more protons and neutrons are in the nucleus, the greater volume the nucleus will have. Okay, so this is protons and neutrons. This is like the mass number. Okay. So then if we know that, say, the volume of a sphere, if you recall, is 4/3 pi r cubed, right? We could then say that r cubed, right? The radius cubed is proportional to volume, so r cubed must also be proportional to the number of protons and neutrons that are within a nucleus. Okay, or conversely, we could say r is proportional to the cube root of the number of protons and neutrons in the nucleus. Okay. To make this here an equality, it actually turns out that the radius of a nucleus is equal to a constant times the number of protons and neutrons cube rooted. Okay, and this is an important equation because you can use it to find the nuclear radius. This r naught is called the Fermi radius. Okay, and it's equal to 1.2 times 10 to the minus 15 meters. So what is the Fermi radius? When would the radius of an element be the Fermi radius? Well, it would be with a value of 1. So that would mean there is 1 proton or 1 neutron in the nucleus. If you had an a value of 1, that is hydrogen. Okay, so that's Fermi radius is the nuclear radius of hydrogen. Okay, Enrico Fermi is a really quite notable atomic physicist. He did a lot of his work at the University of Chicago. He had a lab that was underneath the ground at the University of Chicago, and Miss Whistler was actually telling me a few weeks ago that over the summer she got to tour his lab with her dad, and that's pretty rad. Okay, so anyway, if we take this right here and we plug it in for R, right, we get, that the volume of a nucleus is 4/3 pi times the Fermi radius cubed times the mass number. Cool. All right, what are we going to do with that? What's the point? Oh, we wanted to find the nuclear density. Okay, we wanted to find the nuclear density. All right, so if I leave us some room here, nuclear density, we know density, abbreviated with the Greek letter rho, is mass per unit volume. Okay, so the mass of any atom, like we said, is equal to its mass number times the atomic mass unit. All right, divided by our volume from up here, 4/3 pi times the Fermi radius cubed times the mass number. Oh, hey, check that out. The mass number cancels. And what we notice is nuclear density is independent of the element. And that's a giant deal. Okay, so different elements will have different masses, obviously, but their nuclear densities are the same. Okay, and that nuclear density, if you actually were to do this calculation, the nuclear density would be 2.29 times 10 to the 17 kilograms per meter cubed. Okay, and that's a constant. Nucleuses are stinking dense, is what that says. 2.29 times 10 to the 17 kilograms per meter cubed. Dang. All right. So those are some basics about the atom, how we came up with the density, how we can come up with a nuclear radius. And what we want to actually do is kind of put all that stuff together and investigate what happens with nucleuses. There's a idea called radioactivity, something that was noticed at the end of the 19th century by the Curies, Marie and Pierre, in addition to Henri Becquerel. And they found that these nucleuses don't really stay stable, right? They spontaneously emit particles, and they can become different nuclei as a result, right? If you emit like a proton or a neutron, maybe you'll turn into a different element. So there are 3 distinct emissions that take place, alpha, beta, and gamma, and I'm going to have you investigate a couple of these as your homework. All right, so there will be a nuclear processes simulation, couple important terms. You'll see a parent nuclei is the original nuclei prior to decay, and a daughter nucleus is the resulting one after the decay. So take a look at this simulation on the Google Classroom, and here's an additional problem in Oxford and some pages for reference.